So we've seen that we can get a lower limit on the density of the universe, but that's not really telling anything. It looks like there's not enough matter to make it flat, but there could be some more matter we've missed. We've looked at trying to use the geometry of space to work things out, but that's not going to work because there could be evolution in what's going on in space that confuses us. So we're a bit stuck here. What can we do?
Well, one idea is maybe we need to look at how all the matter in the universe affects how the universe actually expands. So that would be one approach.
Yep, so we know that the matter affects the dynamics, how scale factor went with time. With the Friedmann equation, we've done that.
Yeah.
We know that at the moment, space is expanding, so at time t equals today, a of t is getting bigger, so it's sloping up this way. But in the past, it could be one of these three models we've been talking about.
Right, so this is the dynamics of the universe depending on how much stuff there is in the universe. So if the universe is completely empty, gravity's not doing anything, and so the universe just keeps expanding at the same rate.
Yeah. We know that's not true. We know there's at least some matter in the universe.
Well, there might be very, very little amount of stuff. Maybe we're puny and insignificant.
Mm-hmm. And then you've got a curve which, this would be for a universe which has density less than or equal to the critical density, so it goes up and keeps on going out here and either keeps on as a steady line or flattens out but never curves downwards.
Right, and then you have the really exciting universe, the universe which is slowing down so quickly that it literally reaches a maximum size and then goes in reverse. So literally you are weighing the universe depending on how much these lines are curved. The more gravity there is, the faster and harder the lines curve.
Now we can't see the future, but we could in principle look at the past and see which of these curves is going on. So look at how much faster the universe is expanding at the beginning and how rapidly it's slowing down.
So all that we have to do is to be able to look into the past.
And we have a big advantage over the historians here that we can do that because light travels at such a pathetically slow 300,000 kilometers a second. I mean, totally miserable. That means when you're looking at anything at a reasonable distance to an astronomer, you're looking at it not as it is now, but as it was in the past.
Right.
And what we can measure is the redshift. We talked about this extensively in the first course and a little bit earlier in this course. So the redshift is how much the spectral lines have been moved. And that's telling us how much space is expanded, because the line starts off at a certain length, and then if the line is stretched 10%, it's got a redshift of 0.1, and that means the universe is 10% bigger now than it was at the beginning.
And that's because those photons stretch with the expanding universe. They get pulled around as the universe expands, and so...
Yeah. So it turns out that the scale factor when it was emitted is going to be less than it was now, because it's getting bigger. So this is always going to be less than 1, if you assume the scale factor today is 1. And how much less is given by 1 plus the redshift. So if you see a supernova at redshift 1/2, that means it's going to be 1 over 1 plus 1/2, so 1 over 1.5, what's that, about 0.7 or something?
Yeah, 2/3, and so that means the scale factor of the universe is 2/3 of what it is today. Very convenient. And we can measure those redshifts incredibly accurately. 1 part in 100,000, no problem. 1 part in a million even, potentially possible.
Yeah, so redshifts, okay, well, it's easy then, all solved then. We just measure the redshifts for a bunch of things. That tells us how big the universe was in the past.
Well, let's say that's going to tell us the scale factor, but then we need to know the time.
Yes,
Ooh,
that tells us
time.
how far up we are, but it doesn't tell you where you are this way.
So we just need to have a clock on all of our galaxies, and we'll be solved. We just, use our big telescopes, and we'll look at Big Ben or the Moral equivalent, and it'll tell us how many billion years after the Big Bang it is.
Yes, well, that would be nice, but unfortunately no one's put gigantic megaparsec scale clocks on all the supernovae and galaxies out there.
We need to construct one in the Milky Way for other people to have our benefit.
Yeah, I'll try putting that in for the Australian government to fund it.
That's a good proposal.
But we could use distance, because if you know how far away something is, then if it's 100 light years away, the light's been travelling 100 years. If it's 1,000,000 light years away, the light's been travelling 1,000,000 years. So if we know the distance, then we know how long the light's been travelling.
Well, to first order, that distance is a little funny in the universe because the universe is actually expanding, and so we're going to have to be very careful how we do this, but in principle I agree it's possible.
Yes, so you have to worry about what sort of distance. We've already talked about luminosity distances. There are also other sorts of distances in astronomy which have to allow in different ways for the expansion of space and the weird geometry, but we know how to handle all that.
Yeah.
And so for a given cosmological model, we can calculate the actual light travel time distance.
Yep.
So this is a form of distance telling you how long the light's been travelling for. So what we need to do is measure how far away these supernovae or whatever the galaxies actually are.
So
Easy, right?
we just plop down a ruler between me and you, and we're done.
Would that it were so easy.
Yes.
Now, of course, this is the arguably hardest thing in observational astronomy, getting distances. You want to get a fight going between two astronomers, ask them, how did you measure the distance? It's a bit like archaeologists. People think archaeology is all about wandering around tombs, looting giant treasures, but in fact it's endless arguments about the date of some little sherd of pottery or something like this. For astronomers, it's how far away is that galaxy? Is it 14 or 17 megaparsecs away? And that's a good way to get a fight going.
Yeah, and this is what I did for my PhD thesis and eventually did later on in life. And it's a very controversial but a very important part of modern cosmology.
So let's talk you through the traditional way in which distances are measured.